Hello everyone. My name is Ankush. I'm a PhD student at Carnegie Mellon University, and this is joint work with Shaz Qadeer at Facebook. So today I will be talking about exact and linear time gas cost analysis as part of our paper at SAS 2020. Let me begin by giving a very high-level overview of exactly what smart contracts are. So smart contracts are basically just simple programs which enforce the execution of a contract, often between distrusting parties. These transactions or contracts are executed by third-party miners who execute these transactions and store their output on a global ledger, which is also known as the blockchain. And the user of the transaction typically pays for the execution cost of these transactions in terms of gas units. And how is this execution cost computed? Well, there's a set standard which assigns a cost to every operation, and the total cost of the transaction is just the sum of the cost of all the operations that are executed as part of the transaction. So the execution model looks something like this. The user sends the transaction along with some gas to the miner. The miner then executes the transaction, and if the transaction is successful, adds the transaction to a new block and adds this new block to the blockchain. So the blockchain is nothing but a chain of blocks of transactions. And if there is any leftover gas, then it is returned back to the user. However, there is an implicit assumption here that the miner can execute the transaction only if the gas is sufficient. If the user does not provide sufficient gas, then the transaction is simply aborted and the user has to reissue the transaction. And therefore, it is important to statically estimate the gas cost of transactions. And so in response, there are a lot of prior work, such as Gas.deposit or Gasol or Nomos, to compute an upper bound on the gas cost of these transactions. However, we showed that upper gas bounds are actually inadequate because blockchains still need to dynamically track the gas cost of transactions to return the leftover gas to the user. Moreover, the miners, when they decide which transactions to fit in a block, they actually need the exact gas cost, not the upper bound, to determine which transactions to fit in a block. And therefore, despite the benefits of static gas cost analysis, there are these two issues that need to be mitigated. And therefore, we propose that there's actually a need for exact gas cost analysis. Moreover, we showed that this analysis needs to be efficient, otherwise it can itself lead to denial of service attacks. So therefore, we present our tool called Gasbox, which computes the exact gas cost statically and automatically, and it internally relies on NP solver to do that. It infers constant gas bounds in linear time, and therefore it's very efficient. And we showed that this completely eliminates the need for dynamic gas tracking, which actually compensates the overhead incurred by our analysis tool because it gives advantages at runtime, eliminating the runtime overhead. Our analysis is formalized as a Hoare logic style reasoning with an abstract notion of a gas tank. So it looks something like this. The tank before the expression E on the left is phi plus E of E, and the tank after E is phi, where C of E is the cost of executing expression E. So we track the abstract gas tank value while we are symbolically executing the program. But there are two specific challenges here. The first is, how can we compute an exact gas bound in the presence of branches? And the second, if we are only computing constant gas bounds, how do we handle recursion or unbounded computation? So we will look at these challenges step by step. First, let's talk about branching. So I want to take an example of bidding in an auction. So here I have an add bid function which takes a bid map, a bidder, and a bid as arguments. If the bidder already exists in the map, then you simply move the bid back to the bidder. Otherwise, you insert the bidder and the bid into the bitmap. And here, as you will see, the tick in both the branches are different. So the tick here basically simulates a cost model. It basically means that in the then branch, the cost is C move to adder, whereas in the else branch, the cost is C map insert, which are different from each other. And therefore, you cannot determine an exact gas cost statically because different branches have different gas cost. And so how do we solve this problem? Well, we introduce a gas.deposit operation. What does this operation do? At runtime, it deposits the corresponding gas units into the sender's account. So we add a gas.deposit of CMap insert in the then branch, and we add gas.deposit of CMove to adder in the else branch. And therefore, now the cost of then branch is CMove to adder plus CMap insert, and the cost of else branch is CMap insert plus CMove to adder. And both of these quantities are equal. So with these appropriate deposit operations, we can equalize the gas cost of different branches in the program, and then we can compute an exact gas bound. So these deposit operations have additional advantages as well. They can safely return the leftover gas to the sender. They completely eliminate the need of dynamic gas tracking. And moreover, our tool inserts these deposit operations automatically so that there is no burden of them on the programmer themselves. Okay, so that's how we handle branches. How do we handle unbounded computation? So I want to take here an example of a return bids function in the same auction, which actually returns the bids back to their bidders. So in every recursive call, we check that the size of the bid map is greater than 0, and if it is, we remove the first element from the map, and we move this bid back to their bidder. And then we call ourselves recursively. And so you will see that because there is a tick of CMove to adder in every recursive call, the total cost of return bids is CMove to adder times the size of the bid map. And therefore, the gas cost is not a constant. It actually depends on the argument size. So how do we take care of this? Well, we introduce this concept of gas amortization. So the first thing we do is we introduce a new type called gas bid, which actually stores C move to adder gas units inside the bid itself. So we introduce this first class type, gas of n, which basically represents a variable which has n gas units stored inside it. And when we are adding this bid to the bid map, we actually construct this variable g using gas.construct, and then we pack it inside the bid using the pack construct. And therefore, the cost of add bid now has an additional C move to adder in it. So the total cost is 2 times C move to adder plus C map insert. So basically, the bidder is paying for the return of bids in advance by storing these C move to adder gas units inside the bid map itself, and which will eventually in return bids used to pay for the return of the bid. And how is it achieved? Well, here I'm now showing the return bids function with this amortization trick. So here, when we remove the bid map, remove the bid from the bid map, we unpack it to actually get this variable g out, and then we destruct that variable. So destructing the variable actually creates gas units, which is used to pay for the tick operations. And so with that, the cost of return bids is actually just 0 because it already stores all the gas that is needed to pay for the return of the bids. And this amortization technique has additional advantages. First, it simplifies the analysis because we no longer need to track the sizes of the data structures. In addition, the gas bound of return bids, which is just a constant, it cannot actually exceed the block gas limit. So an issue with the earlier non-amortized auction was that the gas cost of return bids depended on the size of the bid map. And if it exceeds beyond a particular threshold, then the gas cost of return bids would actually exceed the block gas limit for a particular transaction. And then that would essentially lock the auction contract with nobody being able to actually access that transaction or execute that transaction. But with amortization, you can actually free up this locking because return bids practically pays for itself. This amortization also leads to more equitable gas distribution schemes because the bidder is paying for the return of their bid in advance. They're paying it themselves. So there is no additional person who has to issue the return bids function. They do not have to pay for the return of every bidder. Every bidder is responsible for the return of their own bid. And finally, we see that even though the gas cost of returning is unbounded, the gas bound is just a constant. And so our analysis is simpler, and therefore it's very, very efficient and can be done in linear time. Another advantage that our tool provides is that it can infer these gas bounds automatically. So in particular, not only can GasBox infer the gas bounds of all the functions, it can also infer the gas that needs to be stored inside the data structures. So for example, here in the gas bit type, we only mention gas of star, which means that the programmer does not need to specify the amount that needs to be stored inside the gas bit. And then our inference tool will actually replace the star with cmove2adder, stating that you actually need to store cmove2adder gas units inside each bit. And so the programmers only need to indicate which data structures actually need to store the gas, but the actual amount is inferred by our tool. So it introduces very, very low programmer burden to inference of these bounds. Formally, our analysis looks something like this. So we have a pre-gas tank value and a post-gas tank value. For tick operations, the pre-gas tank value is phi plus n, whereas post-tank is phi. The same for gas.deposit and the same for gas.construct. So these three operations, take, deposit, and construct, they remove n units from the abstract gas tank, whereas destruct adds n units of gas units to the abstract gas tank if the type of the variable v that we are destructing is gas of n. Finally, to get an exact gas bound, we also require that the post gas after a return must be 0. So just before termination, you have to ensure that your tank actually has 0 gas units involved. So the initial gas tank value would be an exact gas bound. And that is exactly what our soundness theorem states. So our soundness theorem states that for an expression E, if the pre-gas tank is phi and the post-gas tank is phi prime, and at runtime, if E starts with a concrete gas tank mu and ends with a concrete gas tank mu prime, then phi minus phi prime is equal to mu minus mu prime. And so phi minus phi prime here is the static gas cost, and mu minus mu prime here is the dynamic gas cost. And our soundness theorem says that these two must be equal. Okay, so the workflow of our GasBox tool looks something like this. First, the source code is passed in to the parser and the type checker, which will then generate an abstract syntax tree. Then we do some instrumentation on the code. This instrumentation inserts tick operations and it inserts the deposit operations automatically. Then this instrumented code is passed to the gas analysis tool, which replaces these star variables, stars by actual gas variables, and then it runs the analysis tool, the HoRLogic tool, on the program to generate linear constraints on these gas variables. And then these linear constraints are shipped to an LP solver, which solves these linear constraints, gives us back the results, and then we use these the values and substitute the stars with the values that are given to us by the LP solver. And finally, we return the gas bound to the programmer. So two things that are important to note here are that ticks and deposits are automatically inserted by our tool, and our tool relies on a type checker and an LP solver for inference of bounds. Okay, so just to show an evaluation of our system, we ran our Gasbox tool on a bunch of different standard contracts, and here are the results. Here, LOC means lines of code, defs means the number of functions, vars and cons stand for the number of variables and constraints in our LP problem, IMS stands for the inference time in milliseconds, and V of US stands for the verification time in microseconds. So as you will see here, inference is a magnitude, order of magnitude more expensive than verification. So first we do an inference which takes about some milliseconds of time, and once we have done this inference, we substitute it back and then do a final verification to ensure that all the bounds are actually correct. And this verification is very, very efficient. And so this shows that inference, which only needs to be done once, is slightly more complicated, but once the inference has been done, the verification is actually very, very efficient and can be employed both by the miners as well as the users of the Gasbox tool. Okay, so just to conclude, today I talked about this Gasbox tool, which was based on a Hoare logic style gas analysis framework, and there were two core challenges here. One was how do we handle branching, and the other was how do we handle recursion. For branching, we introduced these Gas.deposit operations to equalize the gas cost of different branches. For recursion, we actually introduced gas amortization which stores gas inside data structures, which pays for the cost of these recursive calls. Finally, the inference of gas bounds can be done in linear time, and we showed that this approach actually introduces very low programmer burden, and it completely eliminates gas tracking. So whatever overhead you get from the static analysis of gas is more than compensated by elimination of the gas tracking at runtime. And that concludes my talk. Thank you so much.